This is problem number 1 from the 2021 AP Calc AB and BC exam. It's a calculator question, and they start you off with this table of values. So that if you just kind of inspect the table before you read the problem statement, it seems like our input variable r is being measured in centimeters. We don't have a consistent interval across which r is taken. It'd be nice if it went 0, 1, 2, 3, 4, but then they threw that 2.5 in the middle, so we'll have to be cautious of that as we make our way through some of the pieces of this. And then the function values that we have access to here are milligrams per square centimeters. It seems like density units there across the bottom for the function. And they do tell us that this function represents the density of a bacteria population in a circular petri dish. R is actually going to be the distance that we sit from the center of the dish. And they tell us that f of r is increasing and differentiable. And then, yeah, units of f we've already noticed from the table. They've given us values. Yeah, we know that. Read part A. Any table of values problem is almost always going to have this, a piece similar to this within it. Use the data from the table to estimate f prime of 2.25. So 2.25 would obviously be the middle of this stretch of the r axis. And if I simply apply a slope calculation, an average rate of change calculation, to that set of ordered pairs, so the r values that we've already highlighted and these corresponding function values, applying that average rate of change calculation is going to be a pretty decent estimate for the instantaneous rate of change at 2.25. So I apply that slope calculation. My units for the function values in the numerator are those density units, milligrams per square centimeter. And then my units for the denominator are the units of r, so centimeters. So the calculator's in play, so it's easy enough to get an answer here. It's not that bad to even do it by hand in this case, but we end up with a value of 8 for f prime of 2.25. And I could leave the units how I have them here. The non-simplified version or the simplified version would be milligrams per cubic centimeter. We also want to use the units and interpret what it means within the context. So this is the instantaneous rate of change of the density of the bacteria at the radius 2.25. So the way that I put together my interpretation statement is just that because this is positive, the density of the bacteria is increasing by about, and I use the word about here because the actual rate of change would be the exact value of f prime of 2.25, but we've estimated f prime of 2.25. We didn't have the capability of finding it exactly. So the density of bacteria is increasing by about 8 milligrams per centimeter squared per centimeter at r equals 2.25. One of the biggest issues I notice with interpretations like this is a lack of referencing the significance of the input. It's not the rate of change in general, it's the rate of change at that spot. It's an instantaneous rate of change. Part B says that the mass measured in milligrams of the bacteria is given by this integral expression. We are asked to approximate that expression using a right Riemann sum with subintervals indicated by the data in the table. So this is kind of weird because normally when we do a Riemann sum, we just have the function that we have data points for within the integral. In this case, we have the radius times the function. So this is going to look a little bit weird, but it should make sense once we start getting into the calculation here. So I've copied my 2 pi in, and then I'm estimating the integral with what you see in this set of brackets. So my first interval spans the x-axis from 0 to 1. The width of that stretch of the, I said x-axis, I should have said r-axis. The width of that stretch of the r-axis is 1. My next interval goes from 1 to 2. Width is 1. Next interval goes from 2 to 2.5, width is 0.5, and then 2.5 to 4.5, width is 1.5. So those are pretty easy to establish. You've done that sort of calculation anytime you've computed a Riemann sum, a trapezoidal sum in the past. Now, if I'm doing a right sum, I'm going to have to take the function values from the right ends of each of these intervals. So that'd be not using f of 0 at all, right? Not using that, but using f of 1, f of 2, f of 2.5, and f of 4. Now, the weird thing is, what r values are we going to use in these positions? Well, we're going to use the r values that coincide with the input for the Riemann sum here, the 1, the 2, the 2.5, and the 4. And you see that carried out across this next line, right? So I took the function values from the table in the middle of each of these three-part multiplications that you see. And then I have the R value taken from the value that corresponded to the function value that I was using. Calculator's in place, you can break that thing out and evaluate, and you get 845.088 milligrams for the volume, or mass, I guess I should say, mass of the bacteria. Part C, are we looking at an overestimate or an underestimate from that work that we did back in Part B? Well, they tell us that the function f is increasing. Clearly the values of f that we see are positive. So since f of r is positive and increasing, we're looking at an overestimate, right? The Riemann sum, if I have this stretch of the x-axis or the r-axis, and I have an increasing function that's above the x-axis, as I've drawn into this coordinate plane here, this right endpoint, when I place my rectangle there, is going to give me a rectangle that accumulates slightly too much space, right? The integral itself is supposed to be the exact area between this graph and the x-axis. We get a little bit too much space with each one of these rectangles. And then the last part of this tells us that the density of the bacteria is modeled by this function, g of r, right? So crazy looking function there. For what value of k between 1 and 4 is g of k equal to the average value of g of r on the interval? So the average value of g of r on the interval is going to be the average value of a function calculation. Calculator's in play, so you could get this tossed into the calculator. Now this value is obviously pretty ugly looking. This is not the answer, so I'm carrying all of the digits of accuracy that I can get from the calculator on the line that I just highlighted, because I'm going to have to do another calculation with that number. And the calculation that I'm going to have to do with that number is I'm going to have to try to figure out when g of r is equal to it, right? When does g of r equal that average value of the function across this interval? And so the calculator's in play here. So what I did is I didn't get a screenshot, I just kind of drew a quick sketch of what my calculator was showing. The graph of g of r looks something like this, and then the y equals 9.875, and yes, I did type in every single one of those digits because I didn't want my final answer, which you see at the bottom of the screen here, I didn't want that to be off at the standard, to the position where it had to be, that 3 digits past the decimal standard that the College Board's looking for. So I graphed y equals 9.87, the whole shebang. I found the intersection. Now this is my final answer, so it would be fine to round that off to 3 digits beyond the decimal. So the value of k that we're looking for here is the x value or the r value of that intersection, and that would be 2.497.